construct unit cell. By repeating this unit cell in a three-dimensional space, we can generate lattice. And by adding motif to this lattice, we can have our crystal. So the crystal is nothing but it's a three-dimensional periodic arrangement of atoms in a space. And lattice is a periodic set of points. This periodicity, it can vary in different directions of three-dimensional space, because of which the axis and angles of crystals may have many different values. That is why we need a systematic approach to classify this lattice into different types. We already have two systems in common to classify these lattices, such as 7 crystal systems and 14 Bривי lattices. In this video, I am going to talk about these classifications. Let's understand the 7 crystal systems in detail. While explaining this system, I have taken an identical analogy for 3 edges ABC and 3 interaxial angles alpha, beta, gamma. This analogy I have displayed on my left hand side. So the first crystal system we are going to study is cubic. By looking at the conventional unit cell of this system, it is clear to us that all the edges are of equal length as well as 3 interaxial angle alpha, beta, gamma equals to 90 degree. The second crystal system we have is a tetragonal. If you will look at the conventional unit cell of cubic and tetragonal crystal, you will witness that these two systems have equal lattice parameter except one. The edge length C along z-axis is greater than rest 2. Thus, tetragonal system is characterized by A equals to B not equals to C and alpha, beta, gamma equals to 90 degree. Next we have the orthorhombic crystal system, in which none of the edge is of equal length but 3 axes are mutually perpendicular. Thus, alpha, beta, gamma equals to 90 degree. The fourth crystal system in our list is monoclinic. The conventional unit cell of this system shows A not equals to B not equals to C. In case of this system, 2 axes are mutually perpendicular and third axis is inclined at some different angle. Thus, alpha and gamma equals to 90 degree and beta not equals to 90 degree. Hexagonal crystal system is at number 5 in our list. In this system, A equals to B not equals to C, alpha and beta equals to 90 degree and gamma equals to 120 degree. In rhombohedral crystal system, all the edges are of equal length. 3 interaxial angles are equal but they are not equals to 90 degree. The seventh and the last crystal system in our list is triclinic. In this system, neither the edges nor the angle are equal. So, these are the 7 crystal systems. You really don't have to worry about memorizing these geometrical relations in one go. Gradually, you will get familiarized with all the details of these 7 crystal systems. Let's get acquainted with 14 Bривי lattices. In each crystal system, there are one or more Bривי lattices. But before going through the list of 14 Bривי lattices, let's understand the basic types of lattices. So we have total 4 types of lattices, in which the first one is the primitive. It is also called as simple lattice. The simple lattice is characterized by lattice point only at the corner. The second type is body-centered, in which the lattice points at the corner as well as at the center of the lattice. In face-centered lattice, the lattice points are present at the corner as well as at the center of all faces. The last type is end-centered or base-centered, in which the lattice points are present at the corner as well as at the center of opposite face pair. Let's go through the 14 Bривי lattices with respect to the 7 crystal systems. Here, capital P represents primitive or simple type of lattice. Capital I indicates body-centered lattice. Face-centered lattice is named by capital F, and capital C is used to name the end-centered lattice if end centers are marked on top and bottom faces. You can also use capital A or capital B if end centers are marked on front and back or left and right faces respectively. Primitive type is present in all 7 crystal systems. Body-centered lattice is present only in cubic, tetragonal and in orthorhombic crystal system. F-type lattice is present in cubic and orthorhombic crystal system. whereas orthorhombic and monoclinic crystal has C type of lattice. From this we can say orthorhombic crystal system is the only system which has all 4 types of lattices. We have seen the 7 crystal systems and 14 Riemann lattices, in which edge-centered lattice is absent. So let's find out why edge-centered lattice does not exist in the list. In edge-centered lattice, points will be present at each corner of the lattice as well as at the center of each edge. We have to check why edge-centered lattice does not exist in the list. To understand this, I am going to draw a 3-dimensional geometry. I have converted this drawn 3D geometry into a simple or a primitive lattice by marking all the corner points. Now, let's indicate the x direction in a drawn lattice. Given lattice is having a cubic shape. Thus, each edge is of equal length. We will assume that this edge length is equal to A. We are interested in an edge-centered lattice. Thus, I will convert this simple lattice into edge-centered lattice by marking all the edge centers. Now, let's focus on point A and B. If I move from point A in the x direction, I find nearest neighbor at a distance A by 2. But when I move in the same manner from point B, I don't find anything at a distance A by 2. For point B, the nearest neighbor is located at a distance A. Thus, point A and B are not equivalent because they do not obey the basic rule of lattice translation. We can generate lattice only if the unit cell is repeated through the lattice translation in a given space. In our case, A is a corner point and B is a edge center of a given lattice, and this set of point is not capable of forming any lattice, due to which edge center lattice does not exist in our list.